So I want to talk about exponent properties and scientific notation. So exponents is a method. So using exponents is how we write repeated multiplication. So if I have a raised to the m power, what that means is a times a times a times, right, however many a's we need, right, so that there are m a's multiplying each other. So 10 to the 6th, right, means 10 times itself 6 times. 1, 2, 3, 4, 5, 6. Okay. So when we have exponential expressions, what we have is a base and an exponent. And another word for exponent is power. So we're going to find the base, we're going to identify the power, and then we're going to write it in the expanded form, all multiplied out. So in this first one, 5 to the 2nd. Now, if the exponent is a 2, we will either say 5 to the 2nd or 5 squared. So 5 raised to the 2nd power, we will either say 5 to the 2nd. We don't say the word power usually, but it means 2nd power. Or we can say 5 squared. Okay, so 5 squared. So the base, right, that is the bottom number, the number that keeps getting repeated. So the base is 5, and the exponent, right, is the little number, is the 2. And so 5 to the 2nd power, if we expand that out, is 5 times 5. Okay. So 3a, notice it's in parentheses, and then it's raised to the 4th power. Well, the power goes with whatever is to its left. And so in this case, the parentheses are holding all of that 3a together. And so it's the entire 3a that gets raised to the 4th power. So the base is the entire 3 times a. So 3a is the base, the exponent is 4, and so writing that out expanded, it's 3a times 3a times 3a times 3a, 4 times. Okay. Negative 2 cubed. Again, the negative 2 is in parentheses, so the cubing corresponds to everything inside the parentheses. So my base is the number, negative 2, the exponent is 3. Writing that out expanded, I'll use parentheses to show the multiplication this time just because of the negative signs. So negative 2 multiplying by itself 3 times. Now this next one, I have 10b cubed. So notice how this one's different than the last two we talked about. There aren't any parentheses. So the cubing, to the 3rd power, we can also say to the 3rd, or cubed. Those are the only ones that have special things for us, squared and cubed. So in this case, the cubed is only corresponding to the 3. It only applies to the 3. So my base, cubing, only corresponds to the b. I caught that on my playback. The 3 goes with the b, so the base is the b. The exponent is the 3. The 10 is just a coefficient. We just get that the one time. So to write this expression, 10b cubed, expanded, it's 10 once times b times b times b. Okay? So especially pay attention to the difference between the quantity 3a to the 4th power and 10b cubed, right? The parentheses and what they do for us. So now we're going to go the other way. We have it expanded, and we're going to write it in its exponent form. So I have 6 times 6 times 6 times 6. So the base is 6, right? It's the part that's repeated. And the exponent is the number of times that you have that factor. So this is 6 to the 4th power. 4 is the exponent. I guess I'm kind of need to get my head in the game here. So 6 to the 4th is the exponent form. So on this next one, I have 5 times 5, and then v times v times v. Well, that's kind of odd because I have 2 bases. I'm not quite sure what I'm going to do about that one. I think maybe I'll just do the 5 times 5 for 25, and then v times v times v, so that my base is v, its power is 3. So to write this expression with exponents, I could have 25v cubed. So on this one's a little bit tricky because I have, right, a negative 2, but then I have all these other 2's. So I could think of that as negative 1 times 2 times, so this is that 2, and then 2, 1, 2, 3, 4, 1, 2, 3, 4. So my base is just the number 2, and I have 1, 2, 3, 4, 5 of those all together. But then I have this negative 1 just kind of hanging out in the front. So negative 2 to the 5th. Or you could say when it's like this, the opposite of 2 to the 5th. Okay, so the exponent properties. Product rule. A to the m times a to the n equals a to the m plus n. In words, what we say is if we multiply like bases, like means the same. So if the bases are the same and we're multiplying, we add the exponents. So here, if I have 10 cubed times 10 to the 6th, that is 10 to the 3 plus 6, 10 to the 9th. Quotient rule. If I divide like bases, so a to the m divided by a to the n is a to the m minus n. So the numerator power minus the denominator power. So in words, so if we divide like bases means it's the same letter, the same number, right? What did we do? We subtract the exponents. So again, with numbers, 9 to the 8th divided by 9 to the 5th. So it's still, the base stays the same. So that's important too, right? It's not a 1 over here. It's a 9, same base. And then it's 8 minus 5, or 9 cubed. Okay. Power rule. A to the m raised to the nth power. This is a to the m times n. Powers to powers we multiply, which is what I'm going to say. So powers to powers. So if you have a power and you're raising it to a new powers, we multiply the exponents. So a to the a cubed quantity squared, 10 cubed quantity squared is 10 to the 6th. So here's what I was thinking when I'm phasing. It's like, should I write all of that out for you? So let me see if I can. Here, I've got a green marker real quick. So that it kind of makes sense for this one. So this is 10 cubed squared. So that's 10 cubed times 10 cubed. So now you're multiplying like bases, so you could add the exponents and get to that 6 that way. Okay, so there are a couple of different ways you can think about these. You could also write out each of those, right? 10 cubes is 10 times 10 times 10 times 10 times 10 times 10. So you have altogether 6 tens written, all multiplied out. Okay, product to a power. A times B, here's your product multiplying on the inside, and then that's raised to a power. So this equals a to the m times b to the m. We raise each factor to the power, right? When a product multiplication is raised to a power, we raise each factor to the power. So if I have 1.1 times x, all raised to the 5th power, and I know it's all because it's in parentheses, this is equivalent to 1.1 to the 5th times x to the 5th. And 1.1 to the 5th, let me just see what that might be. Oh, it's pretty long to write. So 1.61051, x to the fifth. Quotient to a power, I know you know what it's going to be, right? A power for the top and a power for the bottom. When a fraction, quotient, right? When the whole fraction is raised to a power, we raise the numerator. I'm going to say top because I'm not going to have much room. Top and bottom to the power. So if I have the quantity 2/3 to the fourth, this is 2 to the fourth over 3 to the fourth. What is that? 16 over 81. So 2/3 times 2/3 times 2/3 times 2/3. Okay, 0 power, a to the 0. Well, this equals 1 for almost every a. Don't have to worry about the times when it's not. Anything, almost, fine print, raised to the 0 power is 1. So 8 to the 0, that's just 1. Something raised to the first power, a to the 1, this is equal to a. So if the exponent is 1, usually we don't write that. I don't know what I'd say to that. I don't know what I'd write out. Anything to the first power is equal to itself. Anything raised to the first power equals itself. So 16 to the first is just 16. Negative exponents. Negative exponents, so a to the negative m. A negative exponent is like a ticket across the fraction line. So a to the negative m equals 1 over a to the positive m. Once it goes across, it gives up its ticket. So a negative exponent means you need the reciprocal, flip it around, of the base. So you take the reciprocal of the base, change colors, it looks like my pen's dying there, reciprocal of the base, and then the power becomes positive. So 10 to the negative 3, that's the same thing as 1/10 to the positive 3. Okay, so those are our exponent properties, and the place where I think they are most useful is when you're talking about scientific notation. So scientific notation is a way to write really big or really small numbers, and you use it or do it using the powers of 10. So just some exponents that maybe you've seen, or some symbols. So nano, like nanobots, nanotechnology. So it goes by the symbol, it's a prefix, right, a little n, and that means 10 to the negative 9. Micro is a mu, so this is like a Greek m, a mu. That's 10 to the negative 6. Milli is 10 to the negative 3. Centi is 10 to the negative 2. And then for the bigger, so these are small things, right, small things. And then if we have larger things, so big things, kilo, like kilometers, kilograms, so that's 10 to the 3rd. Mega or million, right? I mean, maybe we'll use a capital M, that's 10 to the 6th. A billion is 10 to the 9th, and a trillion is 10 to the 12th. So when you go between a billion and a trillion, you're actually going up by, right, 1,000, 10 to the 3rd. So the syntax is just kind of like the way we decide to write it, is equal to a number between 1 and 10 times 10 to the power. Okay. So if I have the number gosh, what is that? A billion, 3,300,000,000. And I want to write that in scientific notation. What I want to do is I want to come up with a number between 1 and 10, so that would be 3.3. And now I need to multiply it by its appropriate power of 10 so that I would get back to 3,300,000,000. So here's how I do it. I do it with a swoop. So I'm just going to put my pen where the decimal currently lives, and I'm going to swoop until I get to the number 3.3. And I'm going to count how many times I swoop. So the decimal lives here right at the end of your number, and I'm going to start swooping. 1, 2, 3, 4, 5, 6, 7, 8, 9 swoops. So 10 to the power of 9. And it's positive. This is a big number, so I want a positive exponent. So this next one, 0.00000555. Okay, so to write that in scientific notation, this is why I like scientific notation, by the way, because my eyes go a little bit blurry when I'm trying to keep track of the zeros and how many I have. So it's 5.55, right? There's our number, times 10 to the, and I'm going to do the same thing. But now I know that I have a small number, so my exponent's going to be negative. So I'm going to go ahead and swoop, and I'm going to stop when I get to 5.5. So here's where it lives now, and I'm going to start swooping. 1, 2, 3, 4, 5 swoops. And I was swooping to the right, so that'll be negative 5. 5.55 times 10 to the negative 5 is equivalent to, is it just a different way to write the number that we started with. Okay, so let's go the other way. So I have 3.3 times 10 to the 8th in decimal notation. So now we need to multiply 3.3 times 10 to the 8th. So that's essentially, right, so what I'm going to do is I'm going to swoop this time to make a big number. I'm going to swoop 8 times. So start with the decimal where it currently lives and swoop 8 times. So I'm going to swoop to the right because I want to make a big number. 1, 2, 3, 4, 5, 6, 7, 8. And I just made all these little troughs. So now what I'm going to do is go through and fill each of those troughs with a 0. Right, those are all the 10s, right? The first 10 made it 33, and then I just add in the next set of zeros. And now I just need to get my commas in there because otherwise I can't tell. 1, 2, 3, 1, 2, 3. So that looks like 330 million. And finally, 1.01 times 10 to the negative 4 in decimal notation. So I give myself a little space, 1.01, negative 4. So I want to get a small number. So I'm going to take my pen, put it where the decimal is, swoop 4 to the left, right? So it goes in the opposite direction when you're going in the, right, going from scientific to decimal. So 1, 2, 3, 4. There's your decimal. I had 3 troughs to put zeros in. So 0.000101. And if you want to do a leading 0, that's kind of helpful sometimes just to make sure, right, you know where everything goes. So using scientific notation can sometimes make arithmetic easier. So if a person has to spend $1 billion in 24 hours, how much does the person have to spend per minute? Wow. Okay, so this is going to have a little bit of our unit analysis and some scientific notation. Okay, here we go. So spend per minute, so dollars per minute is how we're going to set this thing up. But right now I have $1 billion. So 1 billion is 10 to the 9th dollars. And I'm going to do it in 24 hours. But now I need to get from hours to minutes. So remember, we do this by multiplying by 1. We're just going to be clever about how we write 1. So the first thing I need to get from, I guess just hours to minutes. So 1 hour is 60 minutes. So let's see what that is going to be. I'm just looking on my calculator here, and I don't actually see maybe I've got it there, 10 to the 9th. So 24 times 60 for the denominator. So I have 10 to the 9th over 1440. This will be dollars per minute. So 10 to the 9th. I'm going to see if I can get my calculator to do it. So right here, I don't know if you have this calculator. Yeah, it's just this 10 to the x. So I'm going to try that. So I'm going to do 9 and then try that button. Nope, that wasn't it. So that button first. So 10 to the 9 divided by, what did it say? 1440. 1440. Oh my gosh. Okay, so that is 1, 2, 3. So $694. No, $694,444.44 per minute if you're going to spend $1 billion in a day per minute. Okay, so why was that easier? Maybe, well, just trying to punch in $1 billion, keeping track of all of your zeros to make sure you had enough, that can be kind of confusing. So that's why. So the current world population is approximately 7 billion people. So again, 7 billion is 7 times 10 to the 9th. If 1% of them control 50% of the wealth, how many people is that? So what is 1% of 7 billion? So 1% of 7 billion. So 1% as a decimal is 0.01 times 7 times 10 to the 9th. And if you want, you can even turn that, right? So what would 0.01 be in scientific notation? Exactly. So 10 to the negative 2 times 7 times 10 to the 9th. So now I'm multiplying like bases, so I can add those exponents. So that is equal to 7 times 10 to the 7th. So 7 followed by 7 zeros. So 70 million, I guess? 70 million people control 50% of the wealth. It seems like a lot, except when you think that there are, right, 7 billion people altogether. Okay, last. Portland Power and Gas charges approximately 7 cents per kilowatt hour. And a kilowatt hour, it's 1,000 watts for 1 hour. How much would it cost to burn a 100-watt bulb continuously for 30 days? Okay, so let's see where we're going to start. We want to know how much it's going to cost. And we're going to start, what we do know that it's 7 cents per kilowatt hour. So let's write that part down. So 7 cents per kilowatt, and a kilowatt is 1,000 watts, or 10 to the 3rd watts for 1 hour. So let's see, what am I going to do with the 1 hour? Well, we'll go ahead and get to this next part. So I'm going to do this so 7 cents for every 1,000 watts that we use, and we're going to do 100-watt bulb for 30 days. But this is watts per hour, so I need to get between, it must be multiplying like that. So I need to get between hours and days. So let's go ahead and do that. So 1 day is 24 hours. Okay, is everything going to cancel out for me? So my watts, my days. Let's see, this is 7 cents. So I'm going to my answer is going to be in cents, so that's good. So I'm going to have 7 times 100 times 30 times 24 and then divided by 10 cubed. So the 10 cubed, right, that's 3 zeros. So that'll just cancel those final 3 zeros. So 504 cents, or, right, $5.04. Okay, well, I guess scientific notation we could have done without it on that one. But anywho, let's go ahead and practice our exponent properties. We're going to simplify. No negative exponents in your final answer. 5b, the quantity 5b squared times 5b cubed. So the same base multiplied like bases. Add the exponents. So 5b base stays the same. 2 plus 3 is 5. Okay, dividing. Okay, so you can think of this as splitting apart your fraction. So 12/3 times 10 to the 6th over 10 to the negative 3. Might not feel exactly right going that way, but you know if you go the other way, it would be good, because when you multiply fractions, right, you multiply across the top and the bottom. Okay. And then you can reduce the 12/3, that's a 4. And then here's my times. I'm going back and forth between my x's and my dots. So times. Now I'm dividing like bases. The 10s are like bases, so I'm going to subtract 6 minus a negative 3. Minus the negative plus a positive. So 4 times 10 to the 9th. Okay. What about this next one? I have 100 x to the 5th times y divided by 2x quantity squared. So nothing to do on the top yet. I think I need to take care of those parentheses on the bottom. So I have 2x quantity squared. There's a product to a power. So that the exponent 2 pops into the 2 parts. So I'm going to have 4x to the 4th. So now I can divide my numbers. So 4 goes into 125 times. And then I have my like bases. The x's are the ones that are like. I have x to the 5th divided by x to the 4th. So I'm going to subtract 5 minus 4. That's 1. X to the 1st power. And usually if it's a single power, we don't write it. You can. It's not wrong if you do, but usually we don't. And then the y didn't have anybody to combine with. No other like parts there. Okay, 3 more. Here we go. So 72 over 9, that's 8. 8a divided by a. So this a in the bottom, right, has a power of 1, like bases, so we subtract. So that'll be a to the 7th. And then my b's, my b to the 0, that's a 1, so we don't need that. And I have this b to the negative 2 in the top. So the negative exponent takes that b, moves it to the bottom, and becomes a positive 2. Okay, so it's the reciprocal of its base. So the reciprocal of b is 1 over b. Here it is down here, and now its power is positive. All right, here we go. 7 over 14, 1/2, just like we did above, and then 10 to the 9th divided by 10 to the 3rd, so times 10 to the 6th. And what do we have here? 10x to the 4th squared divided by 10. Let's see. Okay, let's do this right parentheses first. So 10x to the 4th squared, that's 10 squared times, and then powers to powers we multiply. So 10 squared x to the 8th divided by, I'll put it as a fraction, 10. So 100 x to the 8th divided by 10 is 10 x to the 8th. Now, exponent properties are going to keep coming up this quarter and next. So just doing some drills on exponent properties can be helpful.